All right, so welcome to the first lecture on the topic of thermodynamics. And this is from the 15th lecture of the 8th week. And we're just going to scratch the surface with understanding the difference between variables, what are state functions, and how can we characterize them as we characterize variables, what are thermodynamic systems, and what is the first law all about. And even in this first video, all of the topics are well represented in questions in exams. So we're not really wasting any time with understanding the basics. The basics are asked about, at least in our course. And what you can expect in the topic of thermodynamics is mainly questions about understanding the different ideas in place and different processes that take place, which is not too difficult. If you break them apart, everything is doable. So let's get started. When we're talking about variables, and obviously thermodynamic relates to processes that take place and relationships between systems. So when we're talking about variables, we need to talk about variables that we can compare between two systems. So we can either add them up between the two systems, or we can't add them up between the two systems. And if we can add them up, we have extensive variables that we can add up between the respective systems, and intensive would be variables that we cannot add up. So I'm going to put it in additive and non-additive. And oftentimes people have a hard time relating what additive and non-additive means, so we're going to give examples. Let's just say that I'm going to write here volume, mass, charge. What I mean by that is, why don't you imagine that we have two rooms here, and they're separated here. They're separated by a door, and nothing gets by that door. I can actually close that door, seal that door tight. It's an ideal seal. And at some point I can say, okay, I'm lifting that door and I'm opening the gap between these two rooms. And let's just say this room has one volume and this has another volume. If I open the door here, I'm pretty much getting a bigger room that has more volume. So I can pretty much add up the volume of these two systems. And what happens when I put this door in and I have certain things. Let's just say I have a table in this room and I have a chair in this room. If I open this door here, I'm going to have a new room that has both a chair and a table. And in that sense, I can also add up mass of two different systems. And obviously you can think about it as, if I have a certain charge here, or even think of it simplified, I have 15 electrons floating here and I have 10 electrons floating here. If I break this barrier, I can have a new room that has 25 electrons, or I can add up the charge as well. And let's consider intensive. And intensive, we can think of intensive properties as, let's say pressure is a classic example. Pressure, also temperature, and they're both really important to understand. And I'm going to talk about temperature quite often because I don't want you to confuse it with heat. So I'm going to make that separation. Think of it like so. I have another room here. The same idea. It has a door that seals it tight, seals it completely. And let's just say that I have 1 atmosphere of pressure here, 1 atmosphere of pressure here, and 1 atmosphere of pressure here. They're both in standard temperature and pressure. They're both standard rooms, maybe in your apartment. They're both under 1 atmosphere. And if I open this door between them, this new room is not going to have 2 atmospheres. It's not going to have 2 atmospheres. I can't really add up and say, oh, my bigger new room is now going to have 2 atmospheres. That's ridiculous. It's not really going to take place. What else can happen? Let's just say that instead of talking about the pressure, I'm in my apartment, and this maybe is my bathroom and this is my living room, right? And I have a ceiling door between them. And obviously it's about, let's say I heated it up and it's nice 20 degrees temperature in both. If I'm going from my living room to my bathroom, to my bathroom and I open this door up, I'm not going to get a new room that has 40 degrees. It's not going to happen. I can't really add up the temperature. I can't add up the temperature. What's important to know is that I can add up energy. And because I can add up energy, energy is essentially heat. Energy is essentially heat. I can add up heat, but I can't add up temperature. What I mean by that is that I can take two different increases in heat and add them up. I don't want to touch on it because it sometimes may be confusing, but just think of temperature and heat are two different things, and temperature is non-additive. And whenever I'm sitting at an exam and they're asking me questions about it, I'm just thinking about this example with these two rooms. Can I add up the chair and the table and the chair? Yes. Can I add up pressure? No. Can I add up temperature? No. So let's keep on going. We're going to talk about state functions, and this is also sometimes a source for confusion. And state functions give us information about the status quo. Status quo, meaning they give us information about what the system is at now. What is quo? What is the system at now? What is the respective properties of the system? And it doesn't tell us how the system got there. And by that, what I mean, let's just say I have a map. You can think of it as a GPS signal, and I have and this is all the streets and different. And maybe there's a park here, and maybe this is the University of Debrecen here, and maybe this is the Palma, and this is the whatchamacallit there, the melange. And I'm opening my GPS signal. My GPS signal tells me, hey guy, you're right here. This is where you are. It doesn't really tell me how I got there. It doesn't really tell me, oh, this is where you are, and in order to get here, you walked all the way from home and you got to this place. It just tells me where I am at the moment. So this is a state function. This is a state function. It tells me what is your property at the moment, regardless of how you got there. So let's discuss what we have as far as state functions. We have four that we need to address. We have internal energy. And if you looked at the minimal explaining what internal energy is, it is quite confusing. But basically what internal energy is the sum of all the energies in the system, sum of all the energies, sum of all the energies in the system, of all the respective particles in the system arising from kinetic motion or other types of energies. As you can think about it, this is the total amount of energy I have in my system. Total amount of energy that I have in my system. And we're going to get to that when we're talking about the first law of thermodynamics. And this does not really tell me how I got to this type of energy. If I have internal energy in the system equivalent to 560 joules, this contains no information as to how did I get to this amount of energy. Very good. And the next state function we're going to discuss is entropy. Entropy, by the way, internal energy denoted by E and entropy denoted by S. And entropy is just the measure of disorder. Measure of disorder. Measure of disorder in the system. And if you think about it, the less disorder I have, the smaller my S here, the more ordered my system is. So when I have a small s, I have an ordered system. Ordered system. When I have a big S, I have a disordered system. Now, what's important to understand is it doesn't really tell me what was my initial disorder, where did I get. It just tells me what is the disorder of my system right now. And this is why it is a state function. And what's important to understand is the range of entropy can only be above zero. Can only be above zero or equal to zero. It cannot be negative. I can have an ideally stable and ordered system, two different things, but I can have a very ordered system. It's at its minimum entropy, but I can't have negative entropy. I can't have a system that is more than completely ordered. We're going to touch about that when we're going to talk about the second law of thermodynamics. And now what we have to discuss is enthalpy. And being that we're only discussing in this course thermodynamic systems at constant temperature and pressure at STP, standard temperature, or I'm not going to say STP, I'm going to say constant temperature and pressure. What the change in enthalpy is really, or enthalpy is really denoted by H, is really the change in heat or the change in energy. And this is all we really need to know, that the change in enthalpy of the system is really the change in heat of that system. And it's obviously a little bit more complex, but it isn't in our course. This is what we really need to know. And the presentations of Professor Vamoshi in the thermodynamic presentation is very, very, very mathy. But what we really need to know is that the enthalpy really means the change in heat, providing that our system is in constant temperature and pressure. And the last thing we have to discuss is the Gibbs free energy. And this is a really important state function. And this gives us information as to the way processes take place and whether or not they are going to occur spontaneously or going to require energy. So I can say the direction that processes would go, the direction they would go. And let's just say I have a hill here. This is my hill, and I have a rock here at this point. I can calculate that the Gibbs free energy of the process of going down is more likely to occur than the process of going up, providing that this rock is right in the middle here. So if I have two occurrences, either going down or going up, the Gibbs free energy of this process is going to be negative. And whenever Gibbs free energy denoted by G, whenever Gibbs free energy is negative, we're talking about a spontaneous process. Spontaneous process, it does not require energy. It is spontaneous. And whenever the Gibbs free energy, just like climbing up the hill, is positive, we can assume that it's not spontaneous. So positive is not spontaneous, and it does require energy. And whenever Gibbs free energy is zero, whenever it is zero, we have an equilibrium. Or in this instance, you can think about it, this rock is placed right here in the middle. It's as likely to go slightly to the right or as it is to go slightly to the left. So whenever Gibbs free energy is zero, we're talking about equilibrium. Or in thermodynamics, this is oftenly referred to as reversible. Reversible. Very good. So these are our 4 state functions, and all of them are extensive. They are all extensive. I'm going to write it here because they may ask about it. Extensive. They are all extensive. So whenever they're asking, give us an example of an extensive property, and then give us an example of a state function, and interpret whether or not it is extensive or intensive. So this is a good idea to know, that I can add all of these up between systems. Very good. And we're going to keep on going. We're going to talk about what systems are, and we should really know this for chemistry. And if we don't, this should be really, really intuitive. I have 3 types of systems in thermodynamics. I have 3 types of systems. I have an open system, and an open system really means that I can exchange matter and heat. I can exchange matter, I can exchange mass, and I can also exchange heat with my environment. And this is what biological systems are. Just going to write biosystems. Biological systems are open thermodynamic systems. If we weren't open, we'd be dead. So a closed system, which is usually what we deal with in chemistry, whereas in biophysics we deal with open systems. A closed system in chemistry says, I'm not going to be able to exchange matter. My system is closed, but I will be able to exchange heat. And this is a closed system. And an isolated system is really more of more of a theoretic concept, whereas you have a system that is totally isolated, no exchanges can occur with its environment, there's no heat and no mass that can that can move around in and out of the system. There's no movement of mass and heat. This is really quite a simple topic. There's not a whole lot I can talk to you about this. And what's important to understand about an isolated system, and I'm going to say it right away, just so I wouldn't forget to mention it in the future. An isolated system's entropy cannot decrease. And that's important to understand. An isolated system's entropy cannot decrease. And hopefully I will remember to discuss it a little bit later and give you the idea why. But just knowing that this is the case is good for now. So when we'll discuss the second law of thermodynamics regarding entropy, we'll discuss that. And what we have left to discuss is the first law of thermodynamics. And the first law of thermodynamics is basically saying energy cannot be created or destroyed, but it can be transformed, And you can think of it this way. Let's just say I have I have a lamp here. This is my lamp. And let's just say it's on my desk. And it's plugged in, and it's going to give me some light. It's going to luminous and give me some light. And you can think of it as if I put my hand here on the lamp, I will get burned. Basically, it's going to be very, very hot. So some of this energy is transformed to heat. The energy is not lost. And when we'll discuss the second law of thermodynamics, we'll discuss what the entropy is in this case. But energy is being transformed. And this can be resolved with a formula. If we're talking about energy, we can talk about the internal energy of a system. So the change in internal energy, and you always see the delta, that means the change in internal energy, because these are state functions. They tell you on the map what is your new location. It doesn't tell you what was your path. It tells you what was your new location. So what is your change in energy? It is given to you by the change in heat plus the change in work, you can say. Basically, this term refers to heat taken by the system, and this is work done on the system. Obviously, you can put a negative here and say work done by the system, but this is the easiest way, is just saying how much heat did I give to my system and how much work did I do to my system. And you can think of it this way. Let's just say I have a piston here. This is a piston. And I have my system right here. This is my system in green. And if I take this piston, and I push it down, I'm going to compress my system. I'm going to compress all the particles in my system. Let's just say I compressed my system. The system now has more energy. It has more energy because it has the energy to expand rapidly. And this is what happens in your everyday engine. So basically, whenever I'm doing work on the system, I am increasing the energy of the system. Accordingly, if the system is doing energy, let's just say the system is expanding. So this is the system. It's going from this state to this state. It's expanding. And when the system is expanding, it is doing work. So work done on the system, when the system is expanding, is going to be negative. The system is losing work. And if the work done by the system is going down, that means the system is doing work. The energy is also lost. So in this case, when we're going from this state, the system is going to do work, and it's going to push up the piston. It's going to lose some energy. And this is basically all you really need to understand, is whenever work is done on the system, my energy increases, and whenever heat is taken by the system, my energy increases. Because I can put, let's just say I have this pot here of soup, and I'm not really, let's just say I have the lid on and it's closed. I'm not really pressing on it, but I can just I can just turn on the heat here and transfer heat to it, and it's going to have more energy, more internal energy to it without pressing down on it. So you can basically take in heat or take in work, and by that you take in energy. And this is the basics of the first law of thermodynamics. Hopefully you found this helpful. See you on the next video.